So today we'll talk about second moment of area or area moment of inertia. Okay, second moment of area or area moment of inertia. So far we have gone through first moment of area, that was integral of y dA. So that is first moment of area. You called it first moment of area, qx or something like that. So this was there that you have gone through. So that had its own utility. Today we'll see where we can utilize why this term has been coined and why this is so important. So the first picture, if you remember, I have shown you a dam, okay, that was flooded with water. Dam was flooded with water and water was acting from one side of the dam. The picture was something like this. All the water, they apply pressure on this surface, one of the surface, from wherever you have the water interface. Okay, so this dam is holding the water in place. Okay, so this is there. So now let us consider this example and try to understand why second moment of inertia is so important. Area moment of inertia. Okay, so yes, so let us begin. Okay, so you see at a depth of y from the surface, let us say your coordinate system is placed like this, x is along this and y is something like this. Okay, so this is your x, this is your y. Okay, so at a depth y, you have a small elemental area delta A. So how much will be the pressure that acts at this point? Rho y and g, rho g and h, as you know. So it depends from the depth from the top surface of the water. So let us say this is your top surface till where you have the water which is filled. Okay, so rho g y is the pressure that is coming on. So pressure into small elemental area will give you the force that acts on this small area. Let us say that also is delta F, that is the small force, elemental force that acts on this area. Mind it, so area moment of inertia, we'll talk about this also, what is this and why this is important. Okay, so now, yes, so this force, overall the total force will now be equal to integral of this, integral of rho g depth small elemental area, integral of that will give you total force that acts on this dam, and it is this is the force that is trying to slide this dam due to the water head. Is it not? So this is quite okay, this is clear. Okay, so now moment, talking about the moment of this will be again force into the depth y is also creating moment that is trying to topple this in its place. Is it not? That is trying to topple this dam in its place about the axis. So how much is that toppling moment? So that is equal to rho g y dA. This is the force, elemental force, into y that will come. Is it not? If you consider this term is basically the momentum, small elemental moment that is trying to topple this. So overall moment will be about axis will be, it is equal to rho g y square dA, rho g y square dA, integral of that. So constant you can extract out because these two are constant. I assume it is homogeneous water. G is constant in a uniform field of gravitation. So these two are constant. So it is y square dA. So this term, the term that appeared here, the second term is quite much significant when we deal with this type of thing. So this is something which is known as second moment of area or area moment of inertia. Okay. So it is moment is equal to rho g times of this is Ix, this is Ix. Okay, so that is what is second moment of area, and it is given by y square dA, y square dA, and it can be written as a ky square. This is quite much analogous to what you have already gone through. Moment of inertia, mass moment of inertia was equal to mr square. R is the distance from the axis of rotation, m is the mass. So if it is in general, you take it was equal to mk square. K was radius of gyration, okay, for complex geometry. Yeah, for different shaped geometry. So it is analogous to that. Over here, moment of area Ix is equal to AKY square. Okay. So radius of gyration Ky is equal to Ix by small Ix by area, total area of this surface, the surface which is in consideration. Okay. So moment of area, if you know, it is Ix. So moment of area by area, total area square root will give you radius of gyration. It is not just analogous, it is exactly with that value it will match. Okay, so if you are calculating, let us assume this is a laminar shape. This is a laminar shape. So mass moment of inertia A can be replaced by replacing A by mass of this lamina. Okay, that is mass of this lamina. Basically this goes because it is, this holds true. What is rho s? Surface mass density. Surface mass density, rho s is equal to mass per unit area, mass per unit area of this laminar surface. Okay, this laminar surface. So if it is a lamina, it goes true. This can be applied. So radius of gyration is exactly the same value. So that is the probably the reason it is also known as area moment of inertia. Okay. Okay. Bigger it is, slower will be the moment. Okay. So it also acts like that. Okay. So anyway, so let us see how it goes further. So now theorem of parallel axis perpendicular axes, theorem of parallel axis and perpendicular axes, they hold true here also. Okay, they hold true here also. So let us see how they can be applied here. So theorem of perpendicular axis, it is also known as polar moment of inertia. So it goes like moment of inertia about the axis which is perpendicular to the plane of this lamina, perpendicular to the plane of this lamina, xy is the plane of this lamina, and passing through a point which is O. O is over here, which is shown. Okay. Yes, if you want to ask something, you can ask, or else you please mute. Yes, Abhinav? Yes, please. It doesn't matter actually. It doesn't matter actually. See, moment will be just a value, no? If it is like this, it can be, moment can be like this. If it is over here, moment can be like this. Ultimately, effect will be the same. Okay, effect will be the same. Okay, ultimately, you will see the same effect because we are not trying to get the torque, how much it is coming about that axis. Okay, so yes, you can take axis over here also, doesn't matter. Okay. Axis can be taken anywhere. This is just a definition because it is easy to take distance from the top and get the force directly like this. Okay, had I taken distance from bottom, so what you would have done? You would have required this total height, no? As till where water is filled, h minus this y you will take, and you will create a complex definition over here. Ultimately, you will reach to the same place. Okay, clockwise moment may turn out to be anti-clockwise moment. So why to do all those stuff? Okay, if you can get this directly. Okay, so that is the reason. So anyway, so this is your polar moment of inertia. So this is a moment of inertia which is about an axis which is perpendicular to the surface of this lamina. okay, the area which is in consideration. Okay, so this is it. So j0, it is given as j0, okay, or iz, okay. So both are equivalent terms, okay, both are equivalent. So that should be equal to r square. This is the distance of this small elemental piece. dA is the small elemental area which is at a distance of x from y axis, y from x axis. Got it? So x square plus y square is equal to r square. So that gives you directly this. So anyway, so this, if you can extend to next, it simply r square can be written as x square plus y square. That can directly give you this. Okay, it can directly give you x square plus y square. So effectively, what was this and what was this? So this is exactly equal to Iy, that is moment of inertia about this axis, right? Iy and Ix. So this is what? This is moment of inertia about this axis, is it not? So yes, so this gives you what? Theorem of perpendicular axis, and it is valid only for laminar bodies, remember. Okay, it can directly be obtained as Iz is equal to Ix plus Iy. So this is nothing new for you all, but term which has come now, which is introduced now, is J0, which is known as polar moment of inertia. Okay, this is applied to solve problems involving torsion of cylindrical shafts. Later on you will use it, and rotation of slabs, or the rotation of this dam also is equal. Okay, so rotation of slabs, okay, torsion about cylindrical shaft, okay, about its axis. These are some places where you will be using it later on. Okay, it is applied to laminar bodies only. Mi is moment of inertia of area, is having only mathematical property with no physical significance, but in case of mass moment of inertia, it had some physical significance. Okay, but this is just a mathematical term which is analogous to moment of inertia, mass moment of inertia, which is analogous. Okay, so this is something which is to be noted. This is theorem of perpendicular axis. Now coming to this, just a sec. Okay, then, so this is J0. J0 is known as polar moment of inertia. You got to know this now. Okay, so let me just click it once again. Yes, so this is polar moment of inertia applied to solve problems involving torsion and rotation of slabs. You have seen, yes, moment of inertia, right? So yes, let us continue to the next slide. So this is what is a parallel axis theorem. It is again, it is going to be analogous to something that you have gone through. Okay, so again, just see this figure, forget about anything that is here. So there is an axis, b bar is the axis about which hopefully you know how much is moment of inertia. That is an axis which passes through the centroid of that piece. This piece, centroid axis, passes through this centroid, and hopefully I know the moment of inertia about this. Okay, and now I want to know the moment of inertia about xx bar. Okay, xx dash. Okay, so y is the distance from that axis, distance from this axis of this elemental piece dA. Okay, if I express it in a similar manner, if I want to find out moment of inertia about xx dash, so it should be equal to this y square dA, integral of that should be moment of inertia, right? This should be the case. Yes or no? Yes, sir. Very good. So y square is equal to y dash plus d whole square, correct? Okay. So now if I expand this, so it will be equal to y dash square dA. I have taken multiplication also, and 2d y dash d dA, sorry, it will be d dA. Okay, that is there, and then integral of d square dA. Next year students won't see this mistake. So this is how it has evolved. Oh, sorry, yes, because it is constant, yes. Because it is constant, I have taken it out also. So yes, this is how it evolves. So anyway, so this 2D has come out because it is a constant. So now I am effectively being left with this. So now let us see the second term, y dash dA is basically, it is moment, it is trying to calculate the moment of inertia about the axis b dash. Is it not? The second term, is, so it is yc into area, and that should be equal to 0. That should be equal to 0 because this is an elemental a small piece dA. Okay, so this is a moment of this area about, b dash. So moment of this area about the axis which passes through the center of gravity is equal to 0. Okay, y dash dA, this term I am talking about. Okay, so this is moment of area about centroidal axis is 0. So this is first thing that you should know. And then y square dA, this second first term, this is equal to moment of inertia about centroidal axis. This is known, this we assume we know this already. Okay, and then the last term d square will come out, that being a constant. So integral of dA will be equal to A, that is the total area of this laminar body. Okay, so effectively the second term 2 dy bar dA, y prime dA integral should be equal to 0. So this effectively gave me again okay, so this effectively gave me Ixx dash is equal to Ic plus Ad square. This is what is theorem of parallel axis. What it says, moment of inertia about an axis is equal to moment of inertia about the axis which is passing through its centroid plus area into distance square of the distance between these two. Is it not? So it exactly appears like a parallel axis theorem that you have studied in your higher school. Is it not? Mass, yes, please tell me. Second term, this term, no? Okay, I'll tell you. This term, what is this actually? Just look that closely, what this is doing. This is y dA integral. What was this? If you remember this, this is moment of area. Is it not? This is moment of an area. But if your moment is to be taken about the axis that passes through the centroid of that shape, if this is the centroid of this shape and I pass a axis which passes through the centroid itself, so what will happen? There will be no moment at all, and that means it will be stable at any location, any orientation. Is it not? Very good. Hope you got it. So this is moment of area. It is similar to moment of mass that you were taking, because this, if it is a lamina and it has mass spread of rho c, as you have seen, both becomes the same. Okay, if I assume homogeneous lamina, is it not? So yes, so hope you got it. This is how. Okay, so these two, parallel axis theorem and perpendicular axis theorem, is valid for this also. Okay, this also applies to solid shapes. Not like our earlier thing, that is moment of perpendicular axis theorem was valid only for lamina, but this one, this is valid also for solid shapes. Yes. Okay. Yes. So let us continue. Okay. Theorem of parallel axis, this we have already seen now. Okay. So now let us find out what would be moment of inertia, area moment of inertia only. If it is a composite area, composite area. So the way you have been doing for the masses, mass, you can also extend the same for this. So moment of inertia of composite area A given about an axis is obtained by adding moment of inertia of component areas, that is A1, A2, A3, as in this case, as in this case. Okay. So you can do those algebraic stuff here. Okay. So moment of inertia of this will be equal to moment of inertia of this plus moment of inertia of this about the same axis. Axis should not change. Got it? So this algebraic equation is true. So moment of inertia of this should be equal to moment of inertia this minus moment of inertia of this disk if it is removed. So because this disk is no more there in this, so you can assume this is removed. Okay. So that is why this negative sign is there. Okay. So these algebraic things you can do with moment of inertia in case of composite areas. Hope these three laws are quite okay and comfortable because it is in line with what we already know in terms of mass. Okay. Yes, sir. Okay, very good. So now let us do one or two examples. Okay, so moment of a standard shape, this shape we have already used earlier, that is a triangle. Okay, using similar triangle, you know, you are going to take a strip at a distance y from axis of rotation. This time axis of rotation is something like this, x dash, that I am trying to do. Okay, I want to find out moment of inertia of this laminar triangle. Okay, so what will be L by B is equal to H minus Y by H. This is using law of similar triangles. So how much will be this L? This L will be equal to, directly you can obtain this. So dA, that is the a strip area. Area of this small strip will be equal to L into dy. L into dy. So how much is L? You can substitute from here and you get this. Got it? So a small elemental area, now you know. Okay, this will be the area. Now what we have to do? We have to find out the moment of inertia, not moment the way earlier we did. So small elemental moment of inertia of this area will be equal to y square dA. Correct? dA is I dy. Here also we have used it. Okay. So we will integrate this from 0 to h. Is it not? So integral total moment of inertia will be equal to integral of y square dA, and that directly can give you this. So you see, this also can be expressed the way we did it. So if you extract this, you can see your area is this, which was sitting inside this one. Is it not? So I have just segregated that area and wrote it like this: AH square by 6. If you remember your old formula, how was that? It was yes, mh square by 6. M was mass. So mass can be replaced by this. So it is AKY square. What is KY? It is radius of gyration, and it is equal to h by root over 6. Is it not? No point solving it taking elemental strip about y axis, that is not required now. Okay, but yes, you can do it that way also. You can take elements like this and still you can integrate all of them and you can get it. Okay, but again you will get two big integrals from here to here and here to here. You will have to integrate them twice, so it is not suggested. Okay, so hope you got it how you can do this. Very simple, exactly similar to mass moment of inertia. Okay. Okay. Now polar moment of inertia of a circular disk. This is a circular disk with center as O. R is the distance of a small element. Again, this is a solid disk. Okay. laminar solid disk, complete disk. Okay, no annular, not like a ring, it is solid disk. Okay, so again total radius of the disk is given, that is r. Strip thickness is taken as dr. Strip thickness is taken as dr. R is the distance of that small elemental strip which is situated at a distance r from the center. Okay, so small polar moment of inertia, or izz, you can say, if this is x, this is y, izz. So about z axis it will be equal to r square dA. How much is dA? dA 2 pi r dr. If you stretch this strip, so this length will be 2 pi r, thickness will be dr, so it is 2 pi r dr. So that is dA. Area of whole disk we know already, this pi r square, otherwise we could have just integrated this and we can obtain that. Okay, we can integrate this and we can get this from 0 to r, but that is not required. We already use our existing knowledge that area of circle is pi r square. Okay, so yes, so J0, now we'll have to integrate this. So it gives me, substituting r square dA 0 to r, you integrate, is it not? So it is directly giving you this, if, and that fetches me Jo is equal to pi r to the power 4 by 2. So this includes the area part of it. This is your area, is it not? So it is a r square by 2 or kz square by kz square into a. So radius of gyration will be equal to r by root 2 and area being this. Got it? Yes. There must be. Yes, please tell me. There is equal to sign missing and everything's mixed up. It is equal to, after dr. After dr, it is 2 pi, yes. There should be equal to sign equal to. Yes, yes, yes. This r cube is extra, it seems. Huh? Okay, yes, yes. It will be equal to in between. It will be equal to in between. So 2 pi will also. Yes, yes. I got it. I got it. So this you see, this is how we evolve. We evolve actually. Next year, students will not see this error. So you know now how it is developed. It is not in a day, in a year. Over the year, see, last batch couldn't find out this. This batch has found out this. So you give yourself a credit today. Okay. So yes, next time when we meet, yes, this correction was done by you. Okay. Thanks a lot for this correction. I'll acknowledge your name on this video if it is uploaded. Okay, just remind me. So this will become a memory for you all now. Okay. Very good. So keep an eye on my video. Try to figure out those errors. I'll acknowledge your name on my video that I am putting, and that will be history. Okay. So that is yes. Not your results though. Don't try to make that as a history. Okay, try to improve over that as well. So yes, these mistakes do happen. It is here. Thanks for this. I'll correct this. Next batch will not see this. And just to ping me your details, I'll put your name in the acknowledgement that this was corrected by so and so student. And yes, that will be a history for you. Okay. Thanks a lot. Okay, so this is something. Am I with this? So keep an eye on my slides if you want to be history. Okay, okay. Am I with respect to its diameters? So it should be equal by symmetry. You know, Ix should be equal to Iy. Is it not? So both are equivalent. So Jo is equal to, by using perpendicular axis theorem, just now we have seen. So Ix plus Iy should give you Jo. So it is giving you this using perpendicular axis theorem. So that is equal to pi r to the power 4 by 4. Okay, so it is this by further 2, Jo by 2. This is another very important result. So you will be using later on. That is, you are either rotating it like this or you want to do some bending on this beam. Okay, that will be used in a strength of material exercise also. Okay, so not just this, there are many other applications. We will see one application here also, and that will go there later on. So if you are rotating it this way, trying to put bending moment here, okay, so that way this particular bending moment will not be of use. Sorry, Jo is not of use. Okay, in that case you will use Ix and Iy, but if you want to rotate it like this, okay, in that case this will be used. Jo will be useful. Polar moment of inertia. Okay, so these are few applications. Okay, so using parallel axis theorem again, if I want to find it about a dash, so it should be Ix, that is axis. This is for lamina, you remember. Okay, so this is the axis about which you know, distance you know, area you know already a. So yes, it will be a r square plus Ix. So it is like this. So it gives you 5 by 4 pi r to the power 4. Okay, got it. So this is just two examples. I demonstrated one polar moment of inertia of a circular disc. We have demonstrated area moment of inertia, not the polar one. Okay, also yes, at least two you have seen today. Okay, next class we'll see product moment of inertia also. Okay, thanks a lot. So let us begin with product moment of inertia again. So product moment of inertia, so far you may not be that very familiar with this during your school days probably, or have you already gone through this also? Product moment of inertia, what it is actually? See, I'll first tell you why it is required actually. I am from robotics background. No, most of the time I do robotics. So things doesn't rotate just about one axis most of the time. Okay, if it is a bottle, it is not going to rotate always like this. If I throw it in space, it can rotate like this. It can also rotate like this. Okay, or it can have a mixed rotation, something like this. Okay, so when there is mixed rotation, when you have more than two axis rotation, so things go very wild. Okay, rotation is very complex. It is not that trivial, mind it, and this will be used while you will be studying dynamics part of it, and that is the reason this product moment of inertia comes into picture. And mind it, once I told you, inertia is not a scalar, not a vector. What it is? It is a tensor. So there is something which is known as inertia tensor, in which you have moment of inertia about x-axis, you have moment of inertia about other axes, y-axis, and you have moment of inertia about z-axis. So this is known as principal moment of inertia. Rest all are product moment of inertia, and that goes here, ixy, ixz. Okay, similarly ix, yy, yz, izx, izy, izz. So this is actually inertia tensor. Okay, this is actually inertia tensor, and the diagonal terms are principal moment of inertia, that is only single rotation. If it is there, you have to consider the one which is in the diagonal. Okay, for pure rotations. For complicated rotations, for multiple direction rotation, you have to use this as a tensor, and multiple direction rotation angular accelerations also. Okay, so it is not just I into omega gives you torque, rather it is torque is again a matrix, and then I is a matrix, omega is also omega x, omega y, omega z. So you have three rotation, I tau is equal to I omega square. So it will be a omega I omega bar, something like this. Okay, there is a term which goes something like this, and that makes it complete. Okay, that makes it complete. So that is how we use it. So torque uses when you try to find out the torque when you have multiple axis rotation, you have to use this type of inertia tensor matrix, not the just the pure rotation inertia. Okay, so that is where it is used, but mind it, over here we are not talking about moment of inertia due to mass. Over here I am talking about moment of inertia due to area, and again this is analogous to the moment of inertia of mass. Okay, so it will be analogous again, and it is also defined in a similar manner. Okay, so now what is product moment of inertia? It is used for problems that involve unsymmetrical cross sections, and in calculation of moment of inertia of rotated axis. Let us say you know moment of inertia about this axis, you know moment of inertia about this axis. These two were principal moment of inertia, and you have to find out moment of inertia about an axis which is inclined to x and y. Okay, you have this angle which is there, and you want to find out moment of inertia about this axis. How will you do it? Okay, so you, in order to do that, you have to use which is known as product moment of inertia. It can be positive, it can be negative, it can be zero, but mind it, the principal moment of inertia, the one which you saw earlier, was only positive. Okay, so that is what, there is some difference. Okay, anyway, as the time comes, we'll tell you where it is used. A few examples I have given. Okay, so this is where I am going to put it forward now. So yes, so this is xy, ixy is equal to integral of x y dA. Okay, so I want to find out moment of inertia xy. Okay, there is nothing called ixy which is shown in this figure, so don't confuse with existing principal axes which are here. It is defined as ixy is equal to xy, both the distances will be taken. Okay, and dA is the area, that is of small elemental area, that will be taken. We'll do by example, we'll demonstrate this by example how to exactly do it. Okay, this is how it is defined. Okay, so if x and or y, any one of this can be the principal axis. Okay, ixy is a inclined axis about which I want to know. Okay, if it becomes either x or y becomes axis of symmetry, product moment of inertia becomes equal to 0. Okay, product moment of inertia becomes equal to 0. Let us say if this gets aligned with one of the axis, then this product moment of inertia will all go equal to 0. Okay, if this gets aligned to this, then also product moment of inertia will become equal to 0. So product moment of inertia is useful in calculating mi of inclined axes. Okay, determination of axis about which mi is maximum or minimum, this also can be done. Okay, so if at all you want to find out, if I am going to rotate this object in space. Okay, so what is the axis about which if I rotate, I'll see the minimum amount of torque that is required to rotate it. Okay, so let us say if I want to find out, again mind it, product moment of area, this is area, it is not mass. In order to correlate, I am giving you this example, so that may be helpful. Okay, so maximum or minimum, so if at all you want to find out, that may be useful. Okay, because so far you only know mass moment of inertia, so I am every time I am giving you that example so as to correlate. Okay, so now parallel axis theorem for product moment of inertia also holds true, and it is given like this. Parallel axis theorem, if you remember, so ixy is equal to ixy, that is passing through centroid. Yes, and then x bar y bar of A. Okay, x bar y bar of A. X bar is the mean distance, mean y of this centroid. Okay, so that is what is given. Okay, So you can find it out. So this is how you can do it. Okay, so we'll deduce these all results also. So parallel axis theorem for product of inertia can be done like this. Parallel axis theorem, exactly this one. Okay, the one which we have just saw. Okay, so let us say this is your object. Okay, this is your object. Okay, C is the centroid of this object. Okay, and two axes which passes through the centroid is x dash and y dash. This is a small elemental area that is in consideration now in order to find out this. Okay, so you already know moment of inertia about the centroid. Okay, this I assume you know it. Now I have to find out moment of inertia about any inclined axis. Okay, when you have this as the axis. Okay, so now Ixy will be equal to integral of xy dA. How much is x? It is x plus x bar. Y will be equal to y plus y bar dA. These are some small deductions which will help you to understand few things. Okay, so now I will split them all. So it gives me this first term, second term. This is a constant. This is a constant which has come out again. X bar is a constant that will come out. Okay, this x bar y bar. So this will give me directly the area. Now again, what I am going to do, you know very well. What is this and why this is equal to 0? The second term, yes, yes, this is moment of an area about an axis which is passing through centroid. This is again the same similar term. Okay, so these two terms will go to 0. Okay, so you will be left with this and this. Okay, so that quickly will give you Ixy bar and this. Okay, the first term is product moment of inertia about centroidal axis. First term is product moment of inertia about centroidal axis. Second, third terms represent first moment about centroidal axis. They reduce to 0. Third term, simply I have converted this to A and I got this result. Got it? This is how parallel axis theorem for this can be derived. Okay, done. Okay, so there is an example which will demonstrate this more clearly. Okay, so now with this example, determine the product of inertia of right angle triangle which is shown here, base of which is b, h is height that is given with respect to x axis and y axis. We have to find out product moment of inertia, two major axes which are given as x axis and y axis. B, with respect to centroidal axis parallel to x axis and y axis. So there is a centroid, you know, it is at h by 3 from here, b by 3 from here. So axis has to pass somewhere over here and you have to find out product moment of inertia for that. Okay, so hope you got the question now. Let us begin. Okay, so by geometry you can quickly obtain this. Y is equal to, y is what? Y is at a distance this, probably it is taken. Okay, so y varies linearly with x. Y varies linearly with x. Got it? So this was there. So using parallel axis theorem, this is your elemental strip that we are taking. Okay, so moment, this is your product moment of inertia, that will be equal to, for this strip I know, this strip is well known. So dIxy, you just keep watching now. Okay, without intervening here, you will get to know few queries which are arising in you. Okay, so this is directly by parallel axis theorem immediately that we have done. Okay, just few moments back we did for this small strip. This is for this small strip. Got it? Yes, so watch it very, very carefully. So what all terms that goes in? So what is XEL bar? XEL bar is the distance of centroid of this small strip element, centroid of that. So that is the distance. Similarly along Y, so that is there. Okay, and dA is the area of that small strip. So now again move forward. Okay, so d of x bar y bar equal to 0. This is equal to 0 since element is symmetrical about x bar. Element is symmetrical about x bar. So about this axis, it should be equal to 0. Is it not? That is an axis passing through its own centroid, on this element's centroid. Okay, so that should be equal to 0 because that passes through its centroid itself. Okay. Now the next term dA, small elemental area y dx, this is simple. So I have simply used this multiplied by dx should give me the elemental area. Now XEL is x, almost equal to this. You need not to further subdivide it. Okay. YEL will be equal to y by 2. If this is y, so centroid of that will be y by 2. So it gives you directly this. Again I have used this divided by 2. So XEL, YEL is known, that I am going to substitute here. Okay. So immediately as I substitute this, so integral of xy will be equal to this. Now I think there will be plus here, is it not? I didn't give you a chance to do it. It is correct. How? Dixy. If I take integral of this to get this, integral of this goes here. Oh, it is dixy directly. Dixy directly. So it is exactly equal to this. And if I substitute, then this can go here, this will go here. dA is already known, just substitute this. Okay, and then you just do the standard integration, you will get till here. So this directly will give you Ixy, that is equal to 1 by 24 b square h square. This is first result only. This is first result only. Now with respect to centroidal axis, with respect to the centroidal axis, okay, now I will be using x bar and y bar. Okay, this time x bar is, you know, h by 3 and b by 3 distances are there, that is the centroidal axis. Okay, so now I'll use this directly, this equation. So that is telling you Ixy is equal to this plus this. Okay, this is what? About centroid. Very good. About centroid. Yes. So this is what you already know. Just now we did it. Okay. This is the term that can be extracted from here. From here, area you already know the area. 1 by 2 base into a height. Okay. So now you easily can extract using simple algebra. You got something like this. This is what which was desired, and you see this is coming out to be with a negative sign. So it can be negative, don't change the sign, be as it is, leave as it is. Okay, that's all. Okay.